We will round out our discussion by now covering some of the more common continuous distributions. For those who remember the movie Back to the Future, the normal distribution is the flux capacitor of statistics. Many of the inferences we make in statistics would not be possible without the normal distribution. Recall that the tendency of sums and averages of independent observations become normally distributed as the number of samples increases. This is known as the central limit theorem. The PDF for the normal is shown here. Like any other PDF, we must integrate over this function to find probabilities. Unfortunately, the PDF for the normal can only be integrated numerically. For this reason, we standardize our data using the z-score. The standard normal probability density function has mean of 0 and standard deviation of 1. Also note that there is no skewness. Regardless of the mean and the standard deviation, the area under the entirety of the curve will be 1. As the standard deviation falls, the curve will become tall and narrow, like the blue curve. As the standard deviation gets bigger, the curve will get short and wider, like the orange curve. To calculate normal probabilities, we must use a table or technology. With all the distributions, using technology to find the probability is preferable. Let's consider this example. On part A, first convert 36 to a z-score using the given mean and standard deviation. The z-score will be negative 1.125. We can then find the area to the left of 36. This is the same as the area to the left of negative 1.125. Using technology, we arrive at 0.1303. On part B, an area of 10% or 0.1 in the left tail of the normal corresponds to a z-score of negative 1.28. We can use technology to make this determination. Now use the mean and the standard deviation to determine the corresponding battery life at the z-score of negative 1.28 to get 34.76. We will choose 34 months instead of rounding up in order to maintain the 10% criteria. This example illustrates the difference between numerical and statistical rounding. The chi-square is formed from a random variable consisting of the sum of squares of several normally distributed random variables. The PDF is given above, where the Greek letter nu, that looks like a V, is the degrees of freedom. The degree of freedom is sample size minus 1 for the chi-square, students T, and F distributions. The upside down capital L term in the denominator is the gamma function. As you can see, this PDF would be best managed with technology. From the graph, we see how varying the degrees of freedom changes the behavior of the chi-square distribution. Chi-square is one of the family of distributions used to make inferences and construct confidence intervals. It is not applicable to model to physical situations like time to failure. When we explore hypothesis testing, the chi-square distribution will get significant attention. It is particularly useful in assessing the goodness of fit between two distributions. Let's look at this example. In hypothesis testing, we often need to find a critical statistic based on an elected amount of risk. Here, risk is 2%, and we have 12 degrees of freedom. Using technology, this gives us a critical value of 24.05396. The F distribution is another distribution used to make inferences and construct confidence intervals. It is based on the ratio of two chi-square random variables with respective degrees of freedom of nu1 and nu2. The F distribution is used extensively to test for equality of variances from two normal populations. The PDF for the F distribution is very complicated to manage. Thankfully, we have technology to assist us. An important property of the F distribution is illustrated here. The F random variable is based on a risk alpha, a numerator degrees of freedom n1, and a denominator degrees of freedom n2. We can determine the F random variable at risk 1 minus alpha by switching the degrees of freedom and taking the reciprocal. Consider this example. If the critical F statistic is given with alpha at 3% and degrees of freedom noted, we can find the critical F stat with alpha 97% with degrees of freedom switched by taking the reciprocal. The student's t-distribution is formed by combining a standard normal random variable and a chi-square random variable. It is the ratio of a normal random variable and the square root of a chi-square random variable. It has 1 degree of freedom parameter that is associated with the chi-square parameter. The student's t is another distribution used to make inferences and construct confidence intervals. Like the F distribution, the PDF of the t distribution is rather complex and requires the use of technology. The t distribution is equivalent to the F distribution with 1 and n degrees of freedom respectively. The mean of the student's t is 0, and the standard deviation is the square root of the ratio of the degrees of freedom over the degrees of freedom minus 2. As degrees of freedom gets large, the t distribution aligns with the normal distribution with mean of 0 and standard deviation of 1. For this reason, we can use the same standardization technique to find an equivalent z-type score to arrive at a corresponding probability. We will learn that student's t can be one of the most useful and effective statistics due to its accuracy at smaller sample sizes. We see the student's t when assessing differences of mean. Let's consider this example. The mean of the data is 12,585, and the sample standard deviation is 334.21. Since the sample size is 10, the degrees of freedom will be 9. We will use the standardization formula above to find the corresponding t statistic to be 1.56123. Using technology, this gives us a probability of 0.07645. So there is a 7.6% chance that the truck weight will exceed 12,750 on average.